More than 12 billion years ago, something strange was already glowing in the young universe. Through the James Webb Space Telescope, astronomers are finding tiny red objects that look almost like distant stars. Yet some may hide rapidly growing black holes wrapped inside enormous envelopes of dense gas. Scientists call them little red dots, and they may reveal a completely new stage in the birth of the universe's first massive black holes. Tonight, the journey moves slowly across cosmic time to explore what these mysterious objects may really be. If you enjoy calm journeys through the deepest mysteries of space, please like the video, subscribe to the channel, and settle in as the universe quietly unfolds. Far beyond the nearby galaxies and familiar structures of the present-day universe, the light associated with the little red dots begins its journey. During an era when the cosmos is still young, the universe already contains stars, galaxies, gas, dark matter, and growing black holes, yet many of these structures remain less mature than their modern descendants. Space itself continues to expand, stretching the wavelengths of traveling light as immense distances open between regions of matter. By the time this ancient radiation reaches modern observatories, much of it has shifted toward the infrared, carrying information from epochs separated from the present by more than 12 billion years. This distant setting is often described through redshift, a measure of how strongly cosmic expansion has stretched light during its passage across space. Higher redshift generally corresponds to an earlier period of cosmic history. Many little red dots are found at redshifts greater than 4, and examples extend to substantially earlier times. At such epochs, the universe is only a fraction of its current age. Galaxies are assembling rapidly. Stars are forming from reservoirs of cold gas, and massive black holes are beginning or continuing phases of growth. The environment is active in a physical sense, although the vast distances between individual systems remain dominated by dark, expanding space. The early universe is not empty or uniform. Matter gathers into a vast network shaped by gravity and dark matter. Dense regions attract gas, and gas settles into growing galaxies. Smaller systems merge, fresh material falls inward, and new generations of stars enrich their surroundings with elements forged inside stellar interiors. Hydrogen and helium still dominate ordinary matter, while heavier elements become increasingly available as stars live and die. Dust forms from some of these processed elements and begins to influence how radiation escapes from young galaxies. Even modest amounts of dust can change the apparent color of a distant source by absorbing shorter wavelengths and allowing a larger fraction of longer wavelength light to emerge. Against this background, the objects later called little red dots occupy an unusual observational niche. They are associated mainly with the distant universe rather than with nearby cosmic structures. Their apparent abundance rises across part of the early epoch explored by the James Webb Space Telescope, making them relevant to the broader history of galaxy formation and black hole growth. They do not represent every young galaxy, and the name does not define a single proven physical object. Instead, it refers to a population identified by a combination of compact appearance and distinctive colors in deep infrared observations. At the widest scale, their significance begins with timing. Astronomers already know that extremely massive black holes exist surprisingly early in cosmic history. Bright quasars powered by matter falling towards supermassive black holes are observed when the universe is well under 1 billion years old. Building such black holes requires some combination of an initial seed mass, sustained access to gas-efficient accretion mergers, and enough time for growth. The details remain uncertain. Different formation pathways may operate in different environments, and observations continue to test how commonly each pathway occurs. Little red dots enter this larger picture because many appear during periods when early black hole growth is expected to be important. Their existence, therefore, provides a new population through which the young universe can be studied. Some show evidence consistent with active black holes, while others remain harder to classify. The population is still being defined as surveys expand and selection methods improve. Objects chosen by one set of color criteria do not always match those chosen by another, so estimates of abundance depend partly on how the category is constructed. The cosmic surroundings also matter because early galaxies live in an evolving large-scale environment. Some occupy relatively ordinary regions, while others appear within overdensities where neighboring galaxies are more numerous than average. Such regions may provide more opportunities for gravitational interactions and gas inflow, although the connection between environment and little red dot activity remains under study. Observations indicate that at least some examples reside in substantial concentrations of young galaxies. This does not establish a single environmental origin for the whole population, but it places certain objects within regions where structure is assembling efficiently. During these early epochs, the background radiation field and chemical state of the universe also differ from those of later times. Intergalactic hydrogen undergoes a gradual transition from mostly neutral to mostly ionized as the first generations of luminous sources release energetic radiation. This broad process, known as cosmic rayonization, unfolds over an extended interval rather than at one moment. Galaxies and accreting black holes both contribute radiation capable of affecting surrounding gas, although the relative contribution of different source populations remains an active area of research. The little red dots are therefore embedded in a universe undergoing several connected transformations. Galaxies accumulate mass. Stars manufacture heavier elements, dust begins to reshape emerging light, black holes gain material. Ionizing radiation spreads through intergalactic gas. Gravity builds increasingly complex structures from earlier density variations. Each process creates conditions that can influence how a compact, distant source forms and how its radiation travels outward. The great distance also imposes an observational limit. Light reaching Earth records these systems in ancient cosmic time, not in the universe at its much later present age. A source observed at high redshift may have evolved dramatically during the billions of years that follow the emitted light. The observation captures one stage in a continuing history. In this sense, the little red dots are not nearby objects seen faintly. They are records from an earlier universe preserved in radiation that crosses expanding space before entering a telescope. At this outermost level, the central fact remains simple. The little red dots belong to a period when galaxies and black holes are still establishing many of the relationships seen in the later universe. Their compact red appearance is observed from across enormous cosmic distances, but their broader importance comes from the era they inhabit. They emerge amid rapid assembly abundant gas, young stellar populations, changing chemical conditions, and growing gravitational structures. Before any individual dot is examined in detail, its place in cosmic history already makes it a useful marker of how quickly complex systems arise after the beginning of the universe. The ancient light associated with the little red dots reaches the James Webb Space Telescope only after crossing an immense and changing universe. During that journey, cosmic expansion stretches its wavelengths shifting radiation that begins at visible or ultraviolet wavelengths into the infrared by the time it arrives near Earth. This stretching does not merely make distant sources look redder, it also allows an infrared observatory to recover information that would otherwise lie beyond the range of instruments designed mainly for visible light. The James Webb Space Telescope is built to observe this faint, red-shifted radiation with exceptional sensitivity. Its large segmented mirror gathers light from extremely distant sources, while instruments cooled for infrared work separate that light into images and spectra. Deep surveys point Webb toward carefully selected regions of sky and collect photons for long periods. The resulting fields often contain thousands of galaxies at many different distances layered across cosmic time in a single image. Nearby systems appear beside objects whose light began traveling when the universe was still young. These deep fields are not empty windows. Foreground stars nearby, galaxies, distant galaxies, gravitational lenses diffuse background light, and instrumental effects all occupy the same observations. Astronomers, therefore, process the data, carefully correcting detector behavior, removing unwanted signals, aligning exposures, and combining images taken through different filters. Each filter records a range of infrared wavelengths. Together, these measurements produce a rough description of how bright a source appears across the spectrum. For extremely distant objects, this pattern of brightness can provide an initial estimate of redshift. Certain well-known features in a galaxy spectrum move toward longer wavelengths as the universe expands. When one part of the spectrum becomes sharply fainter while another remains detectable, astronomers can compare the pattern with models and infer a probable distance range. This method, known as photometric redshift estimation, is useful for selecting candidates from large surveys. It is efficient, but it is not perfect. Unusual stellar populations, strong emission lines, and active black holes can create colors that resemble those of sources at different distances. Spectroscopy provides a more detailed measurement. Instead of recording broad bands of light, a spectrograph separates radiation into many narrow wavelength intervals. Individual emission and absorption features can then be identified, allowing redshift to be measured with greater confidence. For faint sources, this process is demanding because only a small number of photons may arrive from each object. Webb's infrared sensitivity makes such observations possible for systems that were previously too faint for detailed study. The little red dots become visible within this observational landscape because Webb reaches a combination of depth, wavelength coverage, and angular resolution that was difficult to achieve before. Angular resolution describes how well a telescope can separate small structures on the sky. At the enormous distances involved, even a galaxy spanning thousands of light years can occupy only a tiny apparent area. A compact source may therefore appear nearly point-like, especially when its central region dominates the measured light. Deep infrared imaging also reveals objects that are unexpectedly bright at longer wavelengths compared with shorter ones. Some of these sources satisfy color selections designed to identify little red dots. Their appearance depends on exactly which filters are used and how the selection is defined. As survey teams explore different fields, they apply somewhat different criteria, which means that the boundaries of the population are still being refined. The observing fields themselves influence what can be found. Some web programs examine blank regions chosen to avoid bright foreground objects. Others target massive galaxy clusters whose gravity bends and magnifies the light of more distant systems. This effect, called gravitational lensing, can make extremely faint background objects easier to detect. The magnification is not uniform, and reconstructing the original brightness and size of a lensed source requires careful modeling of the foreground mass. In unlensed fields, astronomers rely more directly on Webb sensitivity and long exposure times. Repeated observations improve confidence that a faint source is real rather than noise. Multiple filters help distinguish genuine high redshift objects from cooler stars or lower redshift galaxies with unusual colors. Even so, classification remains uncertain until stronger evidence is available. A tiny red source can have more than one plausible physical explanation, particularly when only broadband imaging is available. The depth of Webb's surveys creates another challenge. A single apparent object can sometimes contain light from several components that lie close together on the sky. Accurate image modeling is needed to determine whether a source is isolated, blended with a neighbor, or embedded in faint, extended emission. This distinction matters because the measured brightness and color can change if surrounding light is assigned incorrectly. Calibration also plays an important role. Infrared detectors respond differently across wavelength, and telescope optics spread the light of a point source into a characteristic pattern. Astronomers account for this pattern when estimating sizes and separating compact emission from nearby structure. Very small differences in image shape can influence whether an object is described as unresolved or merely extremely compact. As Webb surveys accumulate, the same broad class of red compact sources appears in several independent fields. This repetition shows that little red dots are not confined to a single unusual patch of sky. Their measured abundance still varies with depth selection method and redshift interval, but their presence across multiple programs establishes them as a recurring feature of the distant universe. The process also depends on time. Deep observations made in separate programs can be compared, allowing researchers to check whether measurements remain consistent and whether improved calibration changes earlier conclusions. Survey areas gradually expand, increasing the number of detected sources and reducing the influence of chance variations from one field to another. As the sample grows, astronomers can distinguish common properties from rare ones with greater confidence while still recognizing that the faintest objects remain close to the limits of observation. At this observational scale, the telescope does not yet reveal what each source contains. It records photons' positions, colors image shapes, and, when possible, spectra. From these measurements, astronomers build progressively more constrained interpretations. The path from distant radiation to physical understanding begins with the quiet accumulation of infrared light across deep fields where compact red sources emerge from a background filled with galaxies at many stages of cosmic history. Within the deep infrared fields collected by the James Webb Space Telescope, a particular group of sources begins to stand apart from the surrounding population. They are faint in some bands, brighter in others, and often so compact that their structure is difficult to resolve. Their small apparent size and red color lead to the informal name little red dots. The phrase is descriptive rather than physical. It does not identify what the objects are made of, how they are powered, or whether every object selected under the name belongs to exactly the same class. The word little refers first to appearance on the sky. At the distances involved, even a substantial galaxy can occupy only a tiny fraction of an image. Some of these sources remain unresolved, meaning that Webb cannot clearly separate their light into a larger visible structure. Others are marginally resolved and show evidence of faint extended emission around a bright central concentration. Their compactness is one of the features that makes them unusual when compared with many other galaxies observed at similar epochs. The word red refers to the way their brightness changes across Webb's infrared filters. Their light often rises strongly toward longer observed wavelengths. This red appearance can have several causes. Cosmic expansion shifts the original radiation towards the infrared. Dust can absorb shorter wavelength light. Older or cooler stars can alter the overall color of a galaxy. Strong emission lines can brighten particular filters. Light, produced near an actively accreting black hole, can also shape the spectrum. Because more than one process can create red colors, the color alone does not establish a single physical explanation. Astronomers, therefore, define samples using combinations of measurable properties. Different research groups may require particular color changes between filters, a compact image profile, a minimum signal strength, or a redshift range. These choices are designed to isolate sources that share a recognizable observational pattern. Since the criteria are not completely uniform, one published sample can include objects that another sample excludes. The name Little Red Dot consequently describes an evolving observational category rather than a perfectly fixed population. Despite these differences, several broad characteristics recur. Many candidates are extremely compact in the wavelengths where their red light is strongest. Their central brightness can dominate over any visible surrounding galaxy. Some show a distinctive change in spectral shape, with relatively blue light at shorter rest frame wavelengths and a much redder rise at longer ones. This combination can make the source look unlike a simple dust-reddened stellar population. The apparent size must be interpreted carefully. A telescope does not record a perfect point. Even a distant star is spread into a small pattern by diffraction and the optical system. Astronomers compare the profile of a little red dot with this expected point source pattern. If the source is no broader, its true structure lies below the telescope's resolving power at that wavelength. If it is slightly broader, the data may indicate a compact but extended region. At great distance, this distinction corresponds to physical scales that can still span hundreds of light years. A source that appears point-like is therefore not necessarily small in the everyday sense. It is small relative to what Webb can separate at that redshift. The physical region producing most of the observed light may be much larger than a star and much smaller than a typical galaxy. Brightness adds another part of the puzzle. Some little red dots emit enough light that if the radiation were produced mostly by stars, the implied stellar population would need to be very dense, within a remarkably small region. Early interpretations sometimes produced unusually large stellar masses or extreme stellar densities. These estimates depend strongly on assumptions about the source of the light. If an accreting black hole contributes substantially, then part of the brightness cannot be used to infer stellar mass in the ordinary way. The red sources also differ from common foreground contaminants. Cool stars in the Milky Way can appear compact and red, while dusty galaxies at lower redshift can imitate some high redshift colors. careful photometry, image fitting, and spectroscopy help distinguish these possibilities. A genuine little red dot candidate is usually considered within a broader context that includes its estimated distance, its color pattern, its compactness, and any available spectral features. The population is not perfectly uniform. Some objects are brighter than others, some are more strongly red, some display visible extended structure while others remain dominated by a central point-like component. Some have clear spectroscopic signatures associated with active galactic nuclei, the luminous regions powered by accreting black holes. Others lack equally decisive evidence. This variety leaves open the possibility that the observational category contains more than one physical state or more than one evolutionary pathway. Selection effects also shape the apparent population. Deep surveys are more likely to detect brighter sources than fainter ones. Compact sources can be easier to identify against the background than diffuse objects with the same total luminosity. Color cuts favor objects whose spectra place strong features in particular filters. As a result, the observed sample reflects both the true cosmic population and the methods used to find it. As catalogues grow, researchers compare samples across independent fields to determine which traits remain stable. Repeated detection of similar compact red sources strengthens confidence that the category reflects a feature of the distant universe rather than a survey artifact. The term little red dot remains useful because it allows astronomers to discuss these sources before their physical nature is fully settled. Scientific names often begin this way, with an appearance or behavior becoming recognizable before a complete explanation exists. The label preserves that uncertainty. It describes what Webb detects without requiring every source to share the same internal structure. Across the deep fields, these compact red points become a repeated visual signature of the early universe. Their significance begins not with a confirmed identity, but with a consistent observational impression. They are small on the sky, unusually red across selected infrared wavelengths, frequently dominated by concentrated central light and common enough in certain early epochs to demand careful explanation. At this stage, the evidence defines the population from the outside through the pattern of light that reaches the telescope, while the physical origin of that light remains open to further measurement. Across the early universe, little red dots do not appear with equal frequency at every epoch. Their distribution changes with redshift, which allows astronomers to place the population within a broad sequence of cosmic time. Redshift measures how strongly the expansion of the universe has stretched the light from a distant source. A larger redshift generally means that the observed light began its journey earlier in cosmic history. For little red dots, this measure provides a way to compare their abundance when the universe is young with their abundance at somewhat later stages. Many known examples are found at redshifts of roughly 4 and above, with substantial numbers appearing across the interval when the universe is less than 2 billion years old. Some candidates extend to even earlier periods. The exact range depends on survey depth, selection method, and the reliability of the distance estimate. Photometric measurements can identify likely high redshift sources, while spectroscopy gives more secure values when recognizable spectral features are detected. As more spectra become available, the distribution of the population becomes better defined. The pattern that emerges is unusual. Little red dots seem to become relatively common during a limited part of early cosmic history and then become much less prominent toward later epochs. They are not simply a constant background population visible at all times. Their rise and decline suggest that the physical conditions producing them may be linked to a particular stage in the growth of young galaxies and black holes. The timing does not, by itself, reveal the mechanism, but it provides an important boundary for any explanation. This early interval is a period of rapid change. Galaxies are building stellar mass, drawing in gas and undergoing frequent interactions. Dense reservoirs of material remain available in many systems. Black holes can gain mass if gas loses enough angular momentum to move inward. Star formation can also be intense, filling compact regions with young stars and dust. Little red dots appear during this broader era of active assembly, when several processes capable of generating strong central emission are operating at once. Their abundance is measured by counting objects within known survey volumes. Because a telescope sees only a narrow portion of the sky, researchers estimate how much cosmic space corresponds to a selected redshift interval and then compare the number of detected sources with that volume. This calculation is sensitive to incompleteness. Faint objects may fall below the detection limit, while color criteria may exclude sources that differ slightly from the adopted definition. Corrections are therefore required before a survey sample can be used to estimate the true cosmic population. Small survey areas also introduce cosmic variance. Matter is not distributed uniformly on large scales. One field can intersect a region with more galaxies than average, while another can pass through a relatively sparse region. A sample taken from only one deep field may therefore overestimate or underestimate the average abundance. Combining multiple independent fields reduces this uncertainty and helps determine whether an apparent trend is genuinely cosmic rather than local to one region of sky. As observations accumulate, little red dots continue to appear in different Webb programs. Their repeated detection shows that they are not confined to one survey strategy or one unusual environment. Even so, estimates of their number density still vary because different teams use different definitions. Some selections emphasize very red optical colors. Some require a compact profile and others include specific changes between shorter and longer wavelengths. A broader definition naturally produces a larger sample than a stricter one. The redshift distribution also interacts with telescope sensitivity. At greater distances, a source becomes harder to detect, and only the more luminous members of a population may remain visible. This creates an observational bias toward brighter objects at earlier times. Gravitational lensing can partly offset this effect by magnifying distant sources behind massive foreground structures, but lensing introduces its own uncertainties because the amount of magnification must be modeled. For this reason, abundance estimates from lensed and unlensed fields are often treated with different corrections. Another important feature is the apparent rarity of comparable objects in the nearby universe. Compact red sources do exist at low redshift, but the particular combination associated with little red dots is not commonly observed in present-day galaxy surveys. This difference suggests that the conditions responsible for the population become less common as the universe evolves. Gas supplies decline in many galaxies. Stellar populations age, large galaxies settle into more stable structures, and the average rate of black hole growth changes over cosmic time. The population may therefore represent a temporary phase rather than a permanent class of object. A single galaxy could pass through such a state and later appear completely different. If the phase is short, many galaxies could experience it even if only a modest number are visible at any one moment. If the phase is long, the observed abundance would imply a smaller number of hosts. Determining the duration requires more than counting sources, so the current observations constrain possibilities without fixing a unique lifetime. The timing also affects interpretations of early black hole growth. If many little red dots contain actively accreting black holes, their abundance would imply that obscured or unusual growth phases are common during a period when massive black holes are assembling rapidly. If a substantial fraction instead derive most of their light from extreme stellar systems, then the same abundance would reveal an unexpected mode of compact galaxy formation. Present evidence increasingly supports black hole activity in many spectroscopically studied examples, but it remains uncertain whether one explanation applies uniformly to the entire population. Across cosmic time, the little red dots therefore form a changing pattern rather than a static one. They emerge frequently in the young universe, occupy a broad but limited redshift range, and become less conspicuous at later times. Their distribution connects them to an era of abundant gas, rapid galaxy growth, and active black hole development. At this scale, the main information comes from when and where they appear. Their timing establishes the cosmic conditions under which the phenomenon is most common, while leaving the detailed nature of each compact source to deeper observations. This chronology gives the population a clear place within the changing architecture of the early universe itself. Within an individual little red dot, the first layer that can be examined is not the central engine itself, but the pattern of light spread across the image. The source often appears extremely compact, sometimes nearly indistinguishable from the point-like response produced by the telescope when it observes an unresolved object. This compact appearance does not reveal the true physical size directly. It shows only that most of the detected light is concentrated within a region too small for Webb to separate clearly at the source's great distance. Every telescope spreads light from a point into a characteristic pattern. This pattern is created by diffraction and by the shape of the optical system. Astronomers model it carefully because a distant source can be compared against it. If the measured profile matches the expected point source pattern, the object is considered unresolved at that wavelength. If the profile is slightly broader, the source may contain extended structure. The difference can be subtle, especially when the object is faint and only a limited number of photons contribute to the image. For little red dots, this comparison often shows that the redder component of the emission is especially compact. In some cases, nearly all of the bright long-wavelength light comes from a central region that remains unresolved or only marginally resolved. This concentration is important because ordinary galaxies usually distribute a large fraction of their starlight across wider areas. A galaxy can still contain a bright nucleus, but when the central source dominates strongly, its light profile begins to resemble that of a point source placed within a much fainter surrounding system. Angular size must then be translated into physical size. At high redshift, a tiny angle on the sky can correspond to hundreds of light years or more. The exact conversion depends on cosmological distance, but the general result is that a source can look point-like while still occupying a region far larger than a single star. Webb therefore places an upper limit on the visible size rather than proving that the emission comes from an object with stellar dimensions. The compactness becomes more striking when brightness is considered at the same time. Some little red dots produce substantial luminosity from a region that appears very small. If that luminosity is assumed to come mainly from stars, the implied stellar density can become unusually high. Dense star clusters do exist, and early galaxies can be more compact than many present-day systems, but the inferred combinations of mass, size, and brightness can challenge simple stellar interpretations in some cases. This difficulty depends on modeling assumptions. The amount of stellar mass inferred from light is not measured directly. It is estimated by comparing the observed colors and brightness with theoretical stellar populations. Age dust metallicity and star formation history all influence the result. If a non-stellar source contributes strongly to the measured light, then assigning all of that light to stars can make the stellar mass appear larger than it really is. The apparent compactness can therefore amplify uncertainty in the physical interpretation. Image fitting helps separate possible components. Astronomers model the bright central profile and test whether an additional extended component improves the fit. When faint surrounding light is present, it may indicate a host galaxy beneath the dominant compact source. In other cases, the available data remain consistent with a single unresolved component. The result can depend on wavelength because different parts of the system may dominate different filters. A further complication comes from neighboring sources and detector noise. A faint companion, diffuse galaxy light, or a background fluctuation can distort the measured profile if it is not modeled separately. Researchers therefore test several fitting methods and compare independent reductions of the observations. Agreement across these approaches increases confidence that the compact appearance belongs to the source itself rather than to the surrounding field or image processing effects alone. Shorter wavelength images sometimes reveal a shape that is less centrally concentrated than the longer wavelength emission. This suggests that the light seen at different wavelengths may not come from exactly the same physical regions. Young stars can contribute strongly at shorter wavelengths, while a compact central source may dominate farther into the infrared. Dust can also alter the balance by absorbing some radiation and redistributing energy. The image profile therefore changes not only with physical structure but also with the origin and processing of the light. Surface brightness adds another constraint. This quantity describes how much light is received from a given apparent area, because cosmological expansion strongly dims the surface brightness of distant extended structures. Faint outer regions become difficult to detect. A little red dot may therefore appear more compact than it would if every low brightness component were visible. Deep observations can recover some of this surrounding emission, but the central component remains easier to detect because its light is concentrated. Gravitational lensing can sharpen the view in certain fields. When a distant little red dot lies behind a massive foreground cluster, the cluster's gravity can magnify and stretch the background image. This can reveal structure below the scale normally accessible in an unlensed field. The improvement is not uniform, and the original source shape must be reconstructed using a model of the lens. Even so, strongly magnified cases can place tighter limits on physical size than ordinary imaging alone. Repeated measurements across filters also help test whether the central appearance is stable. If the source remains unresolved at several wavelengths, the case for a genuinely compact, dominant component becomes stronger. If its measured size changes, the difference may indicate multiple emission regions rather than a single simple object. Instrumental resolution also changes with wavelength, so the comparison requires careful correction before physical conclusions are drawn. The outer light profile, therefore, acts as the first boundary around the unresolved center. It establishes how concentrated the radiation is, how much surrounding structure is visible, and how strongly the source differs from more ordinary galaxies at similar epochs. The observations indicate that many little red dots contain a remarkably compact component that dominates much of their red light. It remains uncertain in every case how much of this compact emission comes from stars' accretion or reprocessed radiation. At this stage, the image defines the scale of the mystery without yet revealing what lies inside the brightest region. Around the brilliant compact center of a little red dot, A much fainter structure can sometimes be separated from the dominant light. This surrounding component is interpreted as the host galaxy, the larger system of stars and gas in which the compact source resides. Detecting it is difficult because the central emission can overwhelm nearby starlight, especially at the wavelengths where little red dots appear most strongly red. The host therefore emerges only when observations are deep enough and when the central light can be modelled with great care. A host galaxy is expected if the compact source contains an accreting massive black hole, because such black holes form and grow within galaxies. Yet, the existence of a host does not mean that it is easy to see. At high redshift, cosmological dimming weakens extended surface brightness strongly, while concentrated nuclear light remains easier to detect. A faint galaxy can therefore disappear beneath a bright central component even when its physical size is much larger than the region producing the central emission. Astronomers attempt to separate these components by modeling the image in several infrared bands at once. The unresolved central source is represented using the telescope's point source pattern, while any broader emission is fitted as an extended structure. If subtracting the compact component leaves a coherent galaxy-shaped signal, the remaining light can be studied independently. In many little red dots, however, the residual emission is extremely faint, asymmetric, or absent within current sensitivity limits. This difficulty has important consequences for estimates of stellar mass. If all of the light from a little red dot is treated as starlight, models can imply a very massive and extremely dense galaxy. When a substantial fraction of the red continuum instead belongs to a compact central component, the infrared stellar contribution falls. Recent analyses that attempt to separate the two components often favor host galaxies with lower stellar masses than early single-component interpretations suggested. Some recent spectroscopic studies support a picture in which the host contributes strongly to particular emission lines, even when the red continuum is dominated by the compact source. Oxygen emission can trace ionized gas associated with star-forming regions in the larger galaxy. Ultraviolet light can also contain a significant stellar contribution. By comparing these features with the redder continuum, researchers can estimate how much radiation comes from the host and how much belongs to the central component. In population studies, the emerging host galaxies often appear consistent with relatively low-mass systems undergoing active or recent star formation. Stellar masses around hundreds of millions of times the mass of the Sun are plausible for many modelled examples, although individual objects vary and uncertainties remain substantial. Such galaxies are not unusually large for the early universe. The unusual feature is that a powerful compact source can dominate their rest frame optical light so strongly that the surrounding stars become difficult to detect. The host can also reveal itself through spatially extended ultraviolet emission. In some little red dots, bluer light spreads farther from the center than the redder light. This broader component can be irregular or offset, resembling the uneven structure commonly seen in young high redshift galaxies. Star formation in such systems is rarely arranged into smooth, settled disks. Instead, bright regions can occur in clumps, disturbed structures, or compact concentrations shaped by gas inflow and gravitational interactions. Hydrogen emission provides another way to examine the larger environment at sufficiently high redshift. Certain hydrogen lines can emerge across scales larger than the compact red source. Because some hydrogen photons scatter repeatedly before escaping their observed position, need not match exactly the place where they were first produced. Extended and asymmetric hydrogen emission can therefore trace gas around the host galaxy, as well as star-forming regions within it. Recent observations of little red dots show that such extended hydrogen emission can resemble that found around ordinary star-forming galaxies at similar redshifts. This suggests that the compact source is not isolated in empty space. It is embedded within a recognizable galactic environment containing stars, ionized gas, neutral gas, and material extending beyond the brightest stellar regions. The surrounding galaxy can appear comparatively ordinary even while its central source produces an unusual spectrum. The relationship between black hole mass and host mass is especially important. In nearby galaxies, the masses of central black holes correlate statistically with properties of their stellar hosts. Some early little red dot studies appeared to place their black holes far above these local relationships, suggesting black holes that had grown much faster than their galaxies. That conclusion remains sensitive to how black hole masses are measured and how much host starlight is hidden beneath the compact source. Newer interpretations can reduce the estimated black hole masses in some objects because broad spectral lines may not arise entirely from rapid orbital motion. At the same time, improved decomposition can lower or refine host mass estimates. The balance between these changes is still being investigated. Observations indicate that some little red dots may indeed contain black holes unusually prominent for their host galaxies, but the size of that difference is not established uniformly across the population. The host also provides a reservoir of material. Young galaxies at these epochs can contain large amounts of gas relative to their stellar mass. Star formation consumes part of that supply, while gravitational processes can move another part toward the center. The presence of a compact luminous source therefore occurs within a larger cycle of gas accumulation, star formation feedback, and central accretion. The host is not merely a faint background around the little red dot. It is the physical environment that supplies matter and shapes the conditions surrounding the compact source. At this scale, Webb begins to separate two visible layers that initially appear blended into one red point. The outer layer is a young galaxy, often faint and actively forming stars. The inner layer is far more concentrated and can dominate the red light. Their contrast explains why the host is so difficult to recover and why early interpretations can change as decomposition methods improve. The little red dot remains visually compact, but beneath that compact appearance lies a broader galactic system whose stars and gas establish the immediate environment of the luminous center across the changing conditions of the early universe. Inside the faint host galaxy, the compact central source is defined most clearly by the shape of its continuum. A continuum is the broad, relatively smooth distribution of light across wavelengths separate from the narrow or broad spectral features produced by individual atoms. In many little red dots, this underlying light does not behave like the spectrum of a simple stellar population. It can appear comparatively blue at shorter rest frame wavelengths and then rise strongly towards the red at longer wavelengths, creating a pronounced change in slope that has become one of the most recognizable properties of the population. Stars' dust and accreting black holes each leave different broad signatures in a spectrum. A population of young hot stars usually produces substantial ultraviolet light. Older stars contribute more strongly at longer wavelengths. Dust absorbs shorter wavelength radiation and can redden the emerging spectrum. An active galactic nucleus can add a compact source of optical and ultraviolet light, whose appearance changes further if dense gas and dust surround it. The observed continuum, therefore, records several possible processes at once. Early attempts to explain the red rise with stars alone sometimes require unusual combinations of stellar age, dust extinction, and stellar mass. Dust extinction describes the loss of light as dust grains absorb and scatter radiation. Increasing the amount of dust can make a model redder, but it also reduces the observed ultraviolet light. Many little red dots retain a relatively blue, shorter wavelength component, while showing a much stronger red component at longer wavelengths. A single, heavily reddened stellar population can struggle to produce both behaviors simultaneously. More complex stellar models can improve the fit by combining populations with different ages and different amounts of dust. A relatively unobscured young population can provide the blue ultraviolet light, while an older or more heavily obscured population contributes the red optical emission. This is possible in a galaxy with uneven dust distribution. Yet in some sources the red component is so compact and luminous that the required stellar density becomes difficult to reconcile with ordinary expectations for a small early galaxy. The continuum also contains information about temperature. A smooth source can sometimes resemble thermal radiation from material with a characteristic effective temperature. The red optical shape of certain little red dots has been compared with radiation from relatively cool, dense material, rather than with the direct spectrum of a conventional active galactic nucleus. Such comparisons do not mean the emitting object is a normal star. They indicate only that the emerging radiation can be processed until its broad spectral form resembles light from a warm, optically thick surface. Optically, thick material is matter through which photons cannot pass freely. Radiation is absorbed, scattered, and emitted repeatedly before escaping. When this happens many times, the original spectrum of the central source can be altered substantially. A very energetic inner source can therefore appear much cooler at the outside because the escaping radiation reflects the conditions of the surrounding material rather than the temperature of the deepest region where the energy originates. This possibility becomes useful for understanding why little red dots can look red without displaying the familiar infrared signature expected from a large amount of warm dust. In many ordinary active galaxies, dust heated by the central black hole produces strong emission at longer infrared wavelengths. Some little red dots appear weaker in this region than simple, dusty active galaxy models predict. The absence of a strong, warm dust component in certain objects suggests that the red continuum may not be caused by dust alone. The shorter wavelength side of the continuum often remains relatively blue. This can arise from young stars in the host galaxy, from scattered nuclear light, or from a combination of both. Separating these contributions is difficult because the source is so compact and distant. Spatial information helps when the blue light appears more extended than the red light, but spectroscopy is needed to determine how each component behaves across wavelength. The continuum shape also changes from object to object. Some little red dots show an especially steep red rise, while others have a smoother transition. Some display a clear minimum between the blue and red components, producing a V-shaped spectral form when brightness is plotted across wavelength. Others are less extreme. This variation indicates that the population is not uniform and that contributions from stars, gas dust, and accretion may differ significantly between sources. Redshift complicates the comparison because the same rest frame wavelength appears in different observed filters for objects at different distances. Astronomers therefore shift the measurements back into the source frame before comparing continuum shapes. This correction allows objects at different redshifts to be examined as though their spectra were observed at the wavelengths at which the radiation was originally emitted. Spectroscopic measurements provide the clearest view because they trace the continuum continuously rather than through a small number of broad filters. Deep Webb spectra reveal that the red rise can persist across wavelength ranges, where simple photometric fitting leaves several possible explanations. The measurements also show that strong emission lines can contribute to broadband brightness, so line emission must be removed or modelled before the true continuum shape is inferred. The energy budget places another constraint. Whatever produces the red continuum must supply enough luminosity to account for the observed brightness while remaining consistent with the source's small apparent size. Stellar models can meet this requirement in some cases, but in others they require extreme conditions. Accretion onto a black hole provides a highly efficient source of energy, yet direct accretion, light alone, may not reproduce the unusual continuum shape. This tension has encouraged models in which energetic central radiation is transformed before it escapes. At this layer, the little red dot is defined by light rather than by a visible physical boundary. The smooth continuum carries the combined imprint of the central power source surrounding matter and the host galaxy. Observations indicate that ordinary stars contribute to at least part of the spectrum, while a compact non-stellar component is favored in many well-studied cases. The exact balance remains uncertain from source to source. What remains clear is that the red continuum is not merely a color. It is a structured record of how energy moves through one of the most compact, luminous environments known in the early universe. Within the compact red continuum, hydrogen begins to provide a more detailed view of the material through which the radiation escapes. Hydrogen is the most abundant element in the universe, and its electrons can occupy a sequence of discrete energy states. When an electron moves between these states, hydrogen can absorb or emit light at particular wavelengths. Groups of these transitions form recognizable spectral series. One of the most important for little red dots is the Balmer series, which involves transitions connected to the second energy level of hydrogen. A strong change in brightness near the Balmer limit is often called a Balmer break. In ordinary galaxies, such a break can arise from stellar atmospheres and can become prominent when a population contains many stars whose temperatures and ages produce strong hydrogen absorption. For this reason, early observations of pronounced breaks in some little red dots initially encouraged interpretations involving dense populations of stars. If the red optical continuum were mainly stellar, the size of the break could help constrain the ages and masses of those populations. The difficulty is that the same region of the spectrum can also be shaped by extremely dense gas. When hydrogen atoms are packed into an environment where collisions and radiation repeatedly change their energy states, a significant fraction of the atoms can remain with electrons in the second level. This excited hydrogen absorbs light below and around the Balmer threshold and can create a spectral discontinuity that resembles a stellar Balmer break. The resulting feature is therefore not automatically evidence for an old or massive stellar population. Deep Webb spectroscopy increasingly supports this dense gas possibility in several well-studied little red dots. Balmer absorption lines appear together with strong emission, showing that hydrogen can exist in multiple radiative conditions along the line of sight. Some absorption is shifted slightly in wavelength relative to the main emission, indicating that the absorbing material can move inward or outward rather than remaining completely static. These motions are usually modest compared with the full width of the broad emission wings. The presence of Balmer absorption requires hydrogen in an excited state, capable of intercepting photons at the appropriate wavelengths. Maintaining a substantial column of such material is easier in a dense environment where radiation is trapped and collisions occur frequently. The gas does not behave like a thin, transparent nebula surrounding an ordinary star-forming region. Instead, photons can interact repeatedly before escaping, allowing absorption, emission, and scattering to reshape the spectrum. Hydrogen recombination lines provide another view of these conditions. Recombination occurs when a free electron is captured by an ionized hydrogen atom and then moves through lower energy states. Each downward transition can release a photon. In relatively low-density nebulae, the strengths of the resulting lines follow patterns that can be calculated under standard assumptions. Little red dots sometimes depart from those simple expectations. Dense, gas-high, optical depth, repeated absorption, and collisions can change how photons are redistributed among different hydrogen transitions. This makes the relative strengths of the Balmer lines especially useful. Hydrogen alpha and hydrogen beta arise from different transitions and do not always experience the surrounding material in exactly the same way. Dust can alter their ratio because shorter wavelength photons are absorbed more efficiently. Dense gas can alter the ratio through additional radiative processes. When both effects are possible, the spectrum has to be treated as a coupled system, rather than as a simple dust screen placed in front of a conventional emission region. The shape of the absorption also matters. Some little red dots show relatively narrow depressions, superimposed on much broader emission structures. Others display more complicated profiles. Higher spectral resolution reveals details that can be blurred together in lower resolution observations. As the measurements improve, Balmer absorption appears to be more common than the earliest samples suggested. This strengthens the evidence that dense excited hydrogen is an important ingredient in at least a substantial fraction of the population. A pronounced break can also form when the gas becomes optically thick near the Balmer threshold. In this state, photons near particular wavelengths encounter enough absorbing material that they cannot travel directly outward. The escaping continuum then depends on where in the gas the photons last interact. Different wavelengths can emerge from different effective depths, producing a sharp change in the apparent continuum, even without a dominant population of evolved stars. The temperature of the gas influences this process because it controls ionization, excitation, and collision rates. The density is equally important. If the gas is too diffuse, excited hydrogen states are not populated strongly enough to produce the observed absorption. If the column is sufficiently large, however, the line of sight can contain enough excited atoms to create both strong absorption and a substantial continuum break. Detailed models, therefore, use the Balmer region as a probe of physical conditions rather than treating it simply as an age indicator. Hydrogen also links the smooth continuum to the emission line spectrum. The same dense environment capable of reshaping the Balmer break can emit large amounts of recombination radiation. Energy entering the gas ionizes atoms, and subsequent recombination converts part of that energy into characteristic lines and continuum light. This means that the apparent red surface of a little red dot can be influenced by gas that is simultaneously absorbing, emitting, and scattering radiation. The exact geometry remains uncertain. The absorbing hydrogen may form layers, clumps, or a more continuous envelope around the compact source. Different sight lines can pass through different columns of material, producing variation from one little red dot to another. Some sources may contain stronger stellar Balmer signatures in addition to dense gas absorption. The observed population does not require every object to have identical internal conditions. At this depth, hydrogen changes from a simple marker of star formation into a diagnostic of the compact environment itself. The Balmer break absorption troughs, recombination lines, and continuum shape all indicate that photons encounter substantial amounts of excited gas before escaping. Observations increasingly favor dense hydrogen as an important cause of the unusual Balmer region spectra in several little red dots, while the relative contribution of stars remains source-dependent. The spectrum, therefore, reveals a layer in which hydrogen is not merely present, it actively determines how the central radiation is transformed on its path outward. Across the spectra of many little red dots, some of the most prominent features are broad emission lines from hydrogen and, in several cases, helium. An emission line forms when atoms release photons at characteristic wavelengths. In a quiet gas cloud, the line can remain relatively narrow. When the emitting material has a wide range of velocities, however, the light is shifted slightly towards shorter or longer wavelengths by the Doppler effect, and the line spreads across a wider interval. In nearby active galaxies, broad hydrogen lines usually arise in compact regions where gas moves under the gravity of a central black hole. The faster the gas moves, the stronger the gravitational field is assumed to be at the characteristic emitting radius. When the width of a broad line is combined with an estimate of that radius, astronomers can infer a black hole mass. Similar methods were naturally applied to the first little red dots, with broad hydrogen lines detected by Webb. Those early measurements produced an intriguing result. If the entire width of the lines represented orbital motion, some little red dots appeared to contain black holes with masses reaching millions or tens of millions of times the mass of the Sun. In several cases, those black holes seemed unusually massive relative to the faint host galaxies around them. The interpretation depends on an important assumption. It requires most of the line width to come from the motion of the emitting gas. The distinction matters because inferred masses can depend strongly on width. Webb spectra now show that this assumption does not always hold. In several of the highest quality observations, the broad wings of hydrogen lines have shapes that are difficult to reproduce with simple Doppler motion alone. Instead of following a smooth profile expected from a broad distribution of orbital velocities, the intensity can decline in a form that is naturally produced when photons are scattered by free electrons. Electron scattering changes a photon's direction and can also change its observed frequency slightly because the electrons themselves are moving thermally. If a photon experiences several interactions before escaping, those small changes accumulate. A line that begins with a relatively narrow intrinsic profile can therefore emerge with broad wings, even when the emitting gas itself is not moving at the extreme speeds implied by the final observed width. This distinction becomes visible in the detailed line shape. Doppler broadening often produces profiles that can be approximated by Gaussian forms or by combinations of components associated with different gas motions. Electron scattering in a sufficiently dense ionized medium can instead generate extended wings with a nearly exponential decline away from the line center. Several carefully observed little red dots show profiles that favor this scattering interpretation. The center of the line is especially informative. When the broad wings are modeled as scattered light, a much narrower underlying core can remain. This intrinsic core represents the emission before repeated scattering alters it. Its width corresponds to slower characteristic motion than the full observed line. If black hole mass estimates use this narrower component rather than the entire broad profile, the inferred masses can fall substantially. For some sources, calculations based on the narrower intrinsic lines suggest black holes between roughly hundreds of thousands and tens of millions of times the mass of the Sun, rather than values up to about 2 orders of magnitude larger derived from the broadest wings. The result does not mean that little red dots lack massive black holes. It means that line width cannot automatically be translated into orbital speed without first determining how the line has been formed and altered. Hydrogen beta and other hydrogen transitions provide independent tests. If scattering dominates related lines, should carry signatures of the same surrounding material, although their detailed shapes can still differ because optical depth absorption and radiative transfer vary with wavelength. Comparing several transitions therefore provides a stronger test than fitting a single line. At least some little red dots and related compact active sources show hydrogen lines whose shapes differ enough that a simple electron scattering model cannot reproduce all transitions simultaneously. In such objects, genuine gas motion absorption resonance effects or additional radiative processes may contribute substantially. The evidence, therefore, supports electron scattering as an important mechanism in many well-observed little red dots, but not as a proven explanation for every broad line in every member of the population. Helium strengthens the analysis because helium lines form under different excitation conditions from the strongest hydrogen lines. Broad helium emission is difficult to explain with ordinary star formation alone when it appears together with the compact red continuum and strong hydrogen features. Its width can also be influenced by scattering. The combination indicates that energetic radiation is interacting with dense gas close to the compact source, even when the exact division between true motion and scattering remains uncertain. Line asymmetry provides another clue. Gas flowing toward or away from the center can shift part of a profile, preferentially to one side. Absorption can remove light from selected wavelengths. Scattering tends to redistribute photons in a more characteristic pattern around the intrinsic line. High-quality spectra allow these effects to be separated gradually rather than treating every broad feature as a single velocity measurement. Broad lines in little red dots therefore retain their importance, but their meaning has changed. They still indicate compact energetic environments, and in many cases they strongly support active black holes. Yet the measured width is no longer regarded automatically as a direct speedometer for orbiting gas. The spectrum records both motion and the journey of photons through surrounding matter. By separating the narrow core from the extended wings, Webb observations reveal that part of the apparent velocity can be created after the photons leave the region where the line itself is produced. At this level, the broad lines become evidence not only of gravity, but also of radiative transfer. Their profiles preserve the imprint of how photons travel, scatter, and escape from the compact source. Observations indicate that electron scattering can dominate the wings in many of the best studied little red dots, while other objects require additional mechanisms. The broad line is therefore not a simple measure of one motion. It is a layered record of emission and propagation within a dense early universe environment. Deeper within the compact source, the broad spectral wings point toward a layer of ionized gas in which free electrons can alter the path and frequency of escaping photons. Ionized gas is plasma, a state in which electrons are no longer bound permanently to individual atoms. In a sufficiently dense plasma, a photon may encounter many electrons before it reaches open space. Each encounter changes the direction of travel and can shift the photon slightly in wavelength because the electrons themselves possess thermal motion. Repeated interactions can gradually spread radiation away from its original frequency. This process is called electron scattering. The individual change produced by one encounter is small when the electrons are not moving at extreme speeds. After many scatterings, however, the accumulated effect can become large enough to reshape an emission line. A narrow line produced deeper inside the source can emerge with extended wings, giving the appearance of much faster gas motion than actually exists in the original line-forming region. The final spectrum, therefore, contains information about both the place where the photon is created and the material through which it later travels. The effectiveness of scattering depends strongly on electron column density. Column density measures how many particles lie along a path through the gas. A small column allows most photons to escape with few interactions. A large column increases the probability that photons will scatter repeatedly. Models applied to several little red dots require very large electron columns if scattering is responsible for their broad wings. Such values imply an environment far denser and more enclosed than the thin ionized clouds commonly found across ordinary galactic regions. Another useful quantity is optical depth. Optical depth describes how difficult it is for radiation to pass through matter without interaction. When the optical depth to electron scattering approaches or exceeds unity, a substantial fraction of photons no longer travel directly outward. Instead, they follow irregular paths composed of repeated scatterings. Their total distance traveled inside the gas can become much greater than the straight distance from the emission region to the surface. The temperature of the electrons determines how strongly each scattering changes the photon frequency. Hotter electrons move faster and produce larger shifts. Cooler electrons cause smaller changes, although repeated encounters can still create broad wings when the optical depth is high enough. Detailed line profiles therefore allow models to constrain combinations of temperature and electron column density. Several combinations can sometimes reproduce similar spectra, so the parameters are not determined independently with complete precision. The shape of the scattering region also matters. A spherical layer, a flattened structure, and a collection of dense clumps can expose photons to different numbers of interactions. Radiation escaping along one direction may cross less material than radiation escaping along another. Little red dots are too distant for this structure to be imaged directly at the required scale, so geometry is inferred indirectly from spectra luminosities and consistency between different emission lines. Compactness places an important constraint on these models. In the strongest electron scattering interpretations, the ionized region must be extremely small on galactic scales with characteristic dimensions measured in light days rather than thousands of light years. A light day is the distance light travels during one day. Such a compact layer can maintain a very large particle column without requiring the enormous total gas mass that the same column would demand if spread across an entire galaxy. High density also changes atomic physics inside the plasma. Electrons collide frequently with ions and atoms. Excited states can be populated differently from those in diffuse nebulae. Photons produced by recombination can be absorbed and emitted again, while line radiation can remain trapped long enough to undergo additional scattering. The emerging spectrum then becomes the result of coupled processes rather than a simple set of photons leaving the place where they were first emitted. The plasma does not have to be completely uniform. Dense inner regions can contribute most of the scattering, while lower density material contributes narrower emission. Clumps can create paths with different optical depths. In such conditions, some photons may escape almost directly, preserving a narrow core, while others wander through much larger electron columns and form broad wings. This mixture naturally produces a spectrum containing both concentrated and extended components. Energy must also be maintained throughout the ionized layer. Free electrons recombine with ions unless sufficient radiation or collisions keep the gas ionized. The observed luminosity indicates that a powerful energy source is available within the compact system. The plasma absorbs part of this energy, converts part into line and continuum emission, and allows another part to emerge after scattering. The radiation field and gas state therefore influence each other continuously. The same material can weaken radiation that would otherwise escape from the innermost source. Photons at different energies interact with the plasma in different ways, so the gas can help explain why some little red dots appear bright in optical wavelengths while remaining faint in other bands used to identify unobscured active nuclei. Not every little red dot requires the same scattering depth. Recent analyses of multiple hydrogen lines show that simple electron scattering models cannot reproduce all observed profiles in some sources. Other studies find that line shapes attributed to scattering can also arise from more complicated distributions of gas moving under gravity. These results limit any universal interpretation. Electron scattering remains physically plausible and appears capable of explaining important features in several high-quality spectra, but its contribution must be tested separately for individual objects. This uncertainty does not remove the evidence for dense, ionized gas. Broad and narrow hydrogen components excited hydrogen absorption, compact emission, and unusual continuum shapes all indicate that radiation travels through material unlike the diffuse gas of a normal star-forming region. The exact amount of line broadening assigned to electrons can vary, while the need for a dense radiative environment remains significant in many interpretations. At this depth, the little red dot becomes a problem of photon transport through plasma. Light no longer follows a simple outward path from source to telescope. It can scatter, change frequency, become absorbed, reappear, and escape only after many interactions. The electron-rich layer therefore acts as an active part of the observed object, altering the spectrum before the radiation begins its long journey across the universe. Inside the electron-scattering plasma, the material can be considered not only as a collection of charged particles, but as a larger, enclosing structure. In several current interpretations of little red dots, this structure forms a dense cocoon around the compact central source. The word cocoon describes a surrounding envelope of gas with a very large column density and substantial optical depth. It does not imply a perfectly smooth shell. The gas may be layered, clumpy, flattened, or interrupted by lower density paths, but in every version, the central region is deeply embedded within matter. The cocoon is inferred rather than directly imaged. At the distances of little red dots, Webb cannot resolve a structure measured on scales comparable to the immediate surroundings of a massive black hole. Its presence is reconstructed from the spectrum. Broad hydrogen wings, excited hydrogen absorption, strong recombination, emission unusual, continuum shapes, and weak emission. At some higher energies can all be consistent with radiation passing through a dense envelope before escaping. No single feature establishes the geometry on its own. The interpretation becomes stronger when several independent measurements point toward the same physical conditions. Density is central to this picture. Gas near an actively accreting black hole can reach conditions far beyond those of ordinary interstellar clouds. Particles collide frequently, atoms remain strongly excited, and radiation interacts repeatedly with matter. The envelope can contain regions that are almost completely ionized, beside zones where some neutral hydrogen survives. Temperature also varies with depth. The outer layers can be cooler than the regions closer to the energy source, even though they remain hot by everyday standards. A large column of gas makes the cocoon opaque to many photons. Opacity means that radiation has a high probability of interacting with matter before passing through it. Different wavelengths experience different degrees of opacity. Some photons are scattered mainly by free electrons, others are absorbed by atoms or ions. Still others encounter processes associated with heavier elements. The emerging radiation, therefore, depends on the total amount of matter and on the exact ionization state along each path through the cocoon. The envelope must also remain compact. If the same enormous column density was spread across a normal galactic scale, the required mass of gas could become excessive. Concentrating the material near the center allows a large optical depth to exist with a more limited total mass. This compact arrangement is compatible with the unresolved or barely resolved appearance of the red central source. The cocoon occupies a region far smaller than the surrounding host galaxy, while still being vastly larger than the event horizon of the black hole that may lie at its center. Gravity helps hold this material close to the center, but gravity is not the only influence. Radiation carries momentum. When photons interact repeatedly with gas, they can push outward. Thermal pressure can also resist inward motion, while rotation can support material against direct collapse. Magnetic fields may contribute in some theoretical models. The true balance among these effects remains uncertain because the envelope cannot yet be mapped directly. Observations constrain the conditions that any successful structure must produce rather than revealing a unique internal arrangement. Gas can continue moving through this environment. Some material may drift inward and ultimately join the accretion flow. Other material may circulate, remain temporarily supported, or escape through lower density directions. Spectral absorption in several little red dots indicates modest gas motions. But the strongest available evidence does not require the entire cocoon to be expelled in a powerful wind. This distinction matters because a long-lived dense envelope is easier to maintain when much of the surrounding gas remains gravitationally connected to the central region. The absence of strong outflow signatures in some high-quality spectra is consistent with a deeply embedded growth phase in which feedback has not yet cleared the surroundings. Feedback is the transfer of energy and momentum from an accreting black hole into nearby gas. In many luminous active galaxies at later cosmic times, feedback can drive large winds and disturb the host galaxy. Little red dots often present a quieter spectral picture, with dense gas still covering much of the central source. It remains uncertain how long such a configuration can persist. The covering fraction describes how much of the central source is surrounded by obscuring material when viewed from different directions. A completely spherical and continuous cocoon would have a covering fraction near unity. Recent line diagnostics suggest that such perfect coverage may be too simple for at least some little red dots. Hard radiation appears able to reach gas outside the densest region in certain objects, implying openings or thinner channels through the envelope. Other directions can remain heavily blocked. This uneven geometry helps explain why individual little red dots are not identical. One sight line may cross a particularly thick part of the cocoon, while another intersects less material. Differences in density, ionization, and orientation can alter the observed continuum and line strengths without requiring completely different central engines. The population may therefore include a family of related structures viewed under different physical conditions. The cocoon also has a boundary that behaves differently from its interior. Deeper layers experience a stronger radiation field and greater trapping. Farther outward, the gas becomes more transparent and photons have a higher chance of escaping without another interaction. There is no requirement for this transition to form a sharp surface. In a clumpy envelope, the effective boundary can vary with wavelength and direction. At this layer, the little red dot is no longer simply a point of unusual color. It becomes a compact system enclosed by a substantial reservoir of gas. The envelope controls how easily radiation leaves, how spectral lines are altered, how ionization is distributed, and how directly the innermost region can be observed. Current observations support dense cocoons around several well-studied little red dots, while the exact shape and universality of those cocoons remain uncertain. The hidden center is therefore surrounded by matter that is not passive. It forms the immediate physical environment through which nearly every escaping photon must find a path. Its density preserves a concealed environment in which gravity, radiation, ionization, and gas pressure remain closely coupled, giving the surrounding matter an active role in determining what Webb can detect from across cosmic history. Within the dense cocoon, radiation no longer preserves the form in which it is first produced. Energy released in the compact interior enters gas that is sufficiently thick to absorb scatter and re-emit a large fraction of the incoming light. The spectrum that eventually escapes can therefore look very different from the radiation generated closer to the central source. Instead of revealing the hottest region directly, the observed continuum can reflect conditions in cooler layers farther outward where photons make their final interactions before leaving the envelope. This transformation is known as radiative reprocessing. A photon entering dense matter may be absorbed by an atom or ion, raising the energy of the particle. That energy can later return to radiation through a different transition and at a different wavelength, a photon may also scatter from a free electron and change direction many times. In sufficiently opaque gas, these processes repeat so often that the emerging radiation loses much of the spectral memory of the original source. The depth from which radiation escapes depends on wavelength. Some photons encounter strong absorption and can leave only from relatively shallow outer layers. Others travel farther through the gas before interacting. The visible surface of the cocoon is therefore not a solid boundary. It is an effective photosphere, a region from which photons have a reasonable chance of escaping without another major interaction. Different wavelengths can have different effective photospheres because the opacity of the gas changes across the spectrum. If energy is deposited deep inside an optically thick envelope, repeated interactions can move the radiation toward a more nearly thermal form. Thermal radiation has a broad, smooth spectrum whose shape depends mainly on temperature. Models developed for little red dots show that an envelope with an effective temperature of several thousand kelvins can produce a red optical continuum resembling the radiation from a cool, stellar photosphere. The resemblance concerns the outgoing spectrum rather than the nature of the central object. This distinction is important. A normal star produces energy through nuclear reactions and radiates from its outer atmosphere. In the cocoon interpretation, the power originates primarily from accretion and is redistributed by surrounding gas before it escapes. The exterior can therefore resemble a stellar surface, while the internal energy source is entirely different. The term black hole star has been used for this proposed configuration because the compact system can display a star-like photosphere around an accreting black hole, although the model remains under active testing. The characteristic temperature is regulated by the balance between luminosity and the size of the effective radiating surface. If the same amount of power escapes through a larger surface, the effective temperature is lower. If the surface contracts while the luminosity remains similar, the temperature rises. Dense envelope models can therefore connect the red continuum with the radius at which trapped radiation finally emerges efficiently. This radius is far outside the black hole itself, but still extremely small compared with the surrounding galaxy. Hydrogen contributes strongly to the reprocessing. Ionizing photons can remove electrons from hydrogen atoms. When electrons later recombine with protons, energy is returned through emission lines and continuum radiation. At high density and large optical depth, the resulting photons may be absorbed again rather than leaving immediately. Collisions can also change the populations of atomic energy levels. The final optical spectrum becomes a product of repeated absorption, emission scattering, and collisional redistribution. These conditions can help explain why the optical luminosity and strong hydrogen emission appear closely connected in large spectroscopic samples of little red dots. If both are powered by the same buried energy source and processed within the same gas envelope, Changes in one component can accompany changes in the other. Observations indicate such relationships, although individual sources show substantial diversity, and the exact gas structure remains uncertain. Reprocessing also changes expectations at higher photon energies. A conventional, unobscured, active galactic nucleus can emit substantial ultraviolet and X-ray radiation from regions close to the accreting black hole. If a thick gas envelope surrounds that region, much of the high-energy radiation may be intercepted before it escapes. The absorbed energy does not simply disappear. It can be redistributed into lower energy photons that emerge in the ultraviolet optical and infrared portions of the spectrum. This offers one possible explanation for the unusual combination of strong optical emission and weak X-ray detections that characterizes many little red dots. Very large gas columns can suppress direct high-energy radiation while allowing reprocessed light to remain bright. The interpretation is not unique, and some sources have been detected at X-ray energies. Current observations indicate that heavy obscuration is common in at least part of the population, while the exact fraction remains uncertain. Dust can participate in energy redistribution farther from the hottest gas. Recent infrared measurements provide evidence that heated dust contributes to the longer wavelength emission of at least some little red dots. This does not require dust to explain the entire red optical continuum. Gas can dominate the inner reprocessing, while dust outside the hottest region absorbs part of the escaping radiation and emits it again at longer wavelengths. The relative importance of these components varies between objects. The envelope must release approximately the energy supplied to it over sufficiently long intervals, unless part of that energy goes into mechanical motion or changing the structure of the gas. Radiation trapped for many interactions takes a longer and more complicated path outward, but the energy can eventually emerge in altered form. This gives the cocoon both an obscuring role and a luminous one. It hides the direct spectrum while creating much of the spectrum that Webb actually observes. At this depth, the red light is therefore understood as processed radiation rather than a transparent view of the center. Photons reaching the outside have passed through an environment capable of changing their wavelengths, directions, and probabilities of escape. The apparent surface is formed by the last stages of this long internal journey. Observations increasingly support strong gaseous reprocessing in several well-studied little red dots, while the degree of thermalization, dust contribution, geometry, and optical depth remain source-dependent. The cocoon acts as a converter across much of the observed optical wavelength range, taking energetic radiation from within and returning a cooler, smoother, redder spectrum to the surrounding universe. Beneath the reprocessing envelope, the strongest clue to the hidden power source comes from the amount and character of ionizing radiation required to produce the observed spectrum. Ionizing radiation carries enough energy to remove electrons from atoms. Young massive stars can generate large quantities of it, but an accreting black hole can create a harder radiation field that extends to higher energies. In little red dots, the combination of hydrogen, helium, oxygen, iron, and other spectral features allows astronomers to test which source can supply the required energy, while remaining consistent with the extreme compactness of the system. Hydrogen provides the broadest foundation. Strong Balmer emission shows that large numbers of hydrogen atoms are repeatedly ionized and then recombine with electrons. The luminosity of these lines requires a sustained source of energetic photons. In some little red dots, the hydrogen emission is so strong relative to the surrounding stellar light that ordinary star formation becomes an increasingly strained explanation for the entire energy budget. The tight relationship between hydrogen alpha luminosity and the red optical continuum also suggests that both are powered mainly by the same compact source rather than by unrelated parts of the host galaxy. Helium adds a stronger test because removing an electron from helium generally requires more energetic radiation than ionizing hydrogen. Broad helium emission is detected in a number of little red dots and related compact sources. Its presence indicates that the radiation field reaches energies capable of maintaining highly excited gas close to the center. Massive stars can produce helium-ionizing photons under some conditions, especially in young metal-poor populations, so helium alone does not prove the existence of a black hole. When it appears together with broad hydrogen emission-dense gas, a compact red continuum and other active galaxy signatures, however, the combined evidence becomes more difficult to reproduce with stars alone. Oxygen lines provide a different view because some of them appear to arise farther from the compact center. In large spectroscopic samples, doubly ionized oxygen can correlate with properties of the host galaxy and may be produced substantially by star-forming regions outside the dense envelope. This distinction is useful. It shows that a little red dot can contain ordinary stellar ionization in its host, while a separate central source dominates the red optical continuum and broad hydrogen emission. The spectrum is therefore a mixture of spatial regions rather than a single uniform cloud. Neutral oxygen can trace denser material closer to the buried source. Certain oxygen transitions become strong when photons are repeatedly absorbed and re-emitted through resonant processes involving hydrogen and oxygen. Observations showing a close connection between neutral oxygen emission and hydrogen alpha support a common energetic origin. Such behavior is naturally produced in dense gas exposed to intense radiation, where line photons are trapped long enough for otherwise weak channels to become important. Iron introduces another useful set of diagnostics. Iron has many closely spaced energy levels and can produce rich forests of emission features when gas is dense and strongly irradiated. Some little red dots show ion emission characteristic of environments affected by an active nucleus. Recent ultraviolet studies also find unusually strong ion-related features in certain compact red sources. These observations are consistent with gas exposed to a powerful central ionizing field, although the exact abundance of ion and the detailed excitation mechanism can remain uncertain. The metal lines do not all originate at the same depth. Some narrow features can form in the host galaxy or in gas outside the thickest cocoon. Broader or denser gas features can arise closer to the center. Their different widths, ionization requirements, and relative strengths therefore map a sequence of physical conditions. The spectrum does not provide a direct image of these layers, but it separates them through the way atoms respond to radiation and motion. The strongest argument for accretion comes from combining these line diagnostics with the total luminosity and small emitting region. Accretion converts gravitational energy into radiation as matter moves toward a compact object. Around a black hole, the available gravitational potential is large, allowing a relatively small flow of matter to generate enormous luminosity. This efficiency provides a natural way to power a bright source contained within a region far smaller than a normal galaxy. If stars alone are required to produce the same luminosity, they must be packed into a very small volume and must also reproduce the unusual continuum broad lines, high gas, density and ionization structure. Some stellar contribution is clearly present in the host galaxies, and unusual stellar populations may influence parts of the spectrum. Current observations do not require stars to vanish from the central regions. They indicate instead that stars alone become insufficient for many of the best observed little red dots. Accretion also helps explain the coexistence of powerful optical emission with weak X-ray detections. A black hole can generate energetic radiation deep inside the system, while the surrounding gas absorbs much of it before escape. The energy is then redistributed into lower energy radiation. The absence of strong direct X-rays, therefore, does not necessarily imply the absence of accretion. It can instead indicate that the central source is deeply buried. The evidence remains uneven across the population, as some little red dots have secure broad lines and multiple ionization diagnostics. Others are known mainly from imaging and low-resolution spectra. A few observations can still be described by extreme stellar models, and recent time domain work finds remarkably little variability in many sources, unlike ordinary active galactic nuclei. That lack of variability may reflect heavy reprocessing, unusually rapid accretion, or another physical state, and it prevents a simple one-to-one comparison with familiar quasars. This interpretation remains provisional because improved spectra can change estimates of density, ionization, and black hole mass, but accretion currently provides a coherent explanation for the combined measurements available today. At this depth, the balance of evidence in many spectroscopically studied little red dots favors a compact accreting black hole surrounded by dense gas. Hydrogen records repeated ionization helium traces, harder radiation. Oxygen separates host and nuclear environments, and iron reveals dense irradiated material. No single line carries the conclusion alone. Together with compactness, luminosity, and reprocessing, the lines form a consistent picture of gravitational energy being released near a hidden black hole and then transformed by the matter around it. At the center of the dense cocoon, the emerging interpretation brings the surrounding gas and the hidden black hole into a single compact physical system. The name black hole star describes this proposed configuration. It is not a conventional star, and it does not contain a stellar surface supported by nuclear fusion. Instead, a rapidly accreting black hole supplies the energy, while a massive envelope of hot, dense gas traps and reprocesses much of that energy before it escapes. From far away, the outer radiating layers can resemble a stellar photosphere, even though the source of power lies much deeper. The black hole itself occupies only a tiny fraction of the full structure. Its event horizon marks the boundary beyond which light cannot escape, but the radiation observed by Webb comes from matter outside that boundary. Gas moving inward releases gravitational energy as it loses orbital energy and angular momentum. Close to the black hole, this process can generate intense ultraviolet and higher energy radiation. In an unobscured active galactic nucleus, part of that radiation can travel outward relatively directly. In the black hole star model, the surrounding gas is thick enough to intercept much of it. The envelope, therefore, becomes an essential part of the luminous object. Photons generated near the accreting black hole enter a region with very large particle columns. Some are absorbed, some scatter from free electrons, and others ionize atoms before their energy is released again at lower frequencies. Repeated interactions spread the energy through the cocoon. By the time much of the radiation escapes, its spectrum reflects the temperature, density, and opacity of the outer gas, rather than the much hotter conditions close to the black hole. This arrangement gives the system a star-like property, without making it a star. A normal star has a photosphere because radiation produced in its interior diffuses outward through opaque material until it reaches layers from which photons can escape. A black hole star can develop an analogous effective surface if the surrounding gas is sufficiently opaque. The resemblance is based on radiative transfer. The internal energy source structure and long-term evolution remain fundamentally different. The scale of the envelope is also unusual. Models consistent with the strongest spectra favor a structure far larger than the black hole horizon but far smaller than a galaxy. Dense ionized gas can occupy regions measured in light days while still remaining unresolved at cosmological distances. This compact scale allows enormous electron columns to surround the source without requiring the gas mass that would be needed if the same density extended through thousands of light years. The gas is not expected to remain motionless. Gravity draws material inward. Radiation pushes on matter, and rotation can delay direct infall. The envelope may therefore contain a mixture of inward-moving gas, circulating material, and slowly escaping matter. Observations of some little red dots indicate only mild neutral outflows consistent with an environment that has not yet been cleared by strong feedback. Such a state may allow the black hole to remain supplied with gas, while the outer cocoon continues to hide the hottest inner radiation. Accretion near the Eddington limit provides one way to maintain the required luminosity. The Eddington limit is the approximate luminosity at which outward radiation pressure on ionized matter balances inward gravitational attraction under idealized conditions. Real accretion flows can be more complicated, and some can exceed this level for periods of time because geometry, opacity, and gas inflow alter the balance. Current analyses suggest that several little red dots may contain black holes growing near this regime, although the exact rates remain model-dependent. The term black hole star is therefore a physical proposal rather than a new fundamental category of celestial object. It describes a phase in which an accreting black hole is so deeply embedded that the surrounding material forms an extended radiating envelope. The black hole and cocoon are linked by a continuous flow of matter and energy. Gas feeds the center gravitational energy powers. Radiation ionizes and heats the cocoon, and the cocoon determines the spectrum that escapes. Recent Webb observations strengthen this interpretation for particular little red dots. The exceptionally detailed spectrum of Glimpse 117 contains many independent spectral features that are consistent with a rapidly accreting black hole buried inside hot, dense gas. Electron scattering signatures excited hydrogen-strong recombination emission, and the behavior of several metal lines can be explained within the same general structure. This convergence is important because a model becomes more persuasive when it accounts for several measurements simultaneously rather than matching only one unusual feature. The evidence does not establish that every little red dot is a black hole star. The observational category contains sources with different colors, line profiles, luminosities, and degrees of spectral detail. Some objects lack the measurements needed to test the cocoon model strongly. Others may contain different mixtures of starlight dust, dense gas, and accretion. Even among sources that host black holes, the geometry and optical depth of the surrounding material can vary. The lifetime of the proposed phase is also uncertain. A dense cocoon cannot necessarily remain unchanged while the black hole gains mass and releases large amounts of energy. Accretion consumes part of the available gas radiation, changes its ionization, and feedback can eventually open channels or remove surrounding material. If the envelope thins sufficiently, the object may cease to display the characteristic little red dot spectrum, even though the central black hole continues growing. Within this interpretation, the apparent stellar surface is therefore an emergent boundary created by opacity rather than solid matter, and its location can shift as density, temperature, ionization, and accretion change, making the visible object a temporary expression of deeper physical conditions. At this depth, the little red dot can be understood as a hidden engine wrapped in its own radiating environment. The black hole supplies gravitational power, but the cocoon determines how that power becomes visible. The resulting object can appear red, compact, and unexpectedly star-like while containing a black hole at its center. Observations now provide strong evidence for this configuration in at least some cases, while its frequency and duration remain uncertain. The black hole star model therefore connects the unusual outer appearance with a physically coherent inner structure, without requiring the name to imply an ordinary star. At the innermost observable level, the little red dot reduces to the problem of a black hole gaining mass inside a dense and luminous environment. The black hole cannot be seen directly. Its presence is inferred from the energy released by surrounding matter from the ionization of nearby gas, and from extreme compactness of the source. Accretion is the process that links these observations. Gas loses angular momentum, moves inward through the gravitational field, and converts part of its potential energy into radiation before crossing the event horizon. The growth rate depends on how much material reaches the black hole and how efficiently accretion converts infalling mass into outgoing energy. If the flow is radiatively efficient, a significant fraction of the gravitational energy escapes as light. If the flow becomes dense, radiation can become trapped and carried inward with the gas, allowing the mass supply to rise faster than the observed luminosity would suggest. These differences make the accretion rate difficult to determine from brightness alone. The Eddington limit provides a reference. It describes an approximate balance between the inward pull of gravity and the outward pressure produced when radiation interacts with ionized matter. A black hole radiating near this level can grow rapidly if gas continues to reach it. Growth above the nominal limit is also possible under some physical conditions, especially when the flow is thick, asymmetric, or able to channel radiation away from the main inflow. Such super-Eddington accretion is studied as one possible route to rapid black hole growth in the early universe. Little red dots are important because many appear during an epoch when there has been limited cosmic time available for black holes to become massive. A black hole that begins from a small stellar remnant must pass through many stages of mass increase to reach millions or billions of times the mass of the Sun. Continuous near-Eddington accretion can accomplish substantial growth, but interruptions slow the process. Larger initial seeds reduce the required number of growth cycles. The observations therefore connect present mass estimates with deeper questions about how the first black hole seeds form. Those mass estimates remain uncertain. Traditional methods use the width of broad emission lines together with luminosity to infer the gravitational influence of the black hole. In little red dots, electron scattering can contribute to the line width, so using the full observed profile as a velocity measurement can overestimate the mass. When scattering is removed from the interpretation, some inferred black hole masses become smaller. The range can still extend from hundreds of thousands to millions, or tens of millions of times the mass of the Sun in well-studied sources. A smaller black hole does not make the early growth problem disappear. Instead, it changes the stage of growth being observed. Some little red dots may represent black holes that are still building towards the masses seen in later quasars. Their high number density can be consistent with a population in which many modest black holes pass through heavily obscured, rapidly accreting phases before a smaller fraction become the extremely luminous quasars detectable across enormous distances. The surrounding cocoon affects how mass and luminosity are inferred. If much of the radiation is reprocessed before escaping, then the observed spectrum does not reveal the intrinsic accretion flow directly. Energy can leave through optical and infrared wavelengths after beginning at much higher energies. The geometry of the gas also changes how much radiation escapes along a particular line of sight. Estimates of the intrinsic luminosity therefore depend on models of opacity, covering fraction and energy redistribution. Black hole spin introduces another uncertainty. Spin changes the structure of the innermost stable orbit and can alter the efficiency with which accretion produces radiation. A rapidly spinning black hole can under some conditions release more energy per unit mass accreted than a slowly spinning one. For a fixed observed luminosity, a more efficient flow requires less mass to be added each moment. Over long periods, this affects the growth history. Present little red dot observations do not generally determine spin directly. The supply of gas remains equally important. A black hole cannot grow rapidly if its host fails to deliver material to the center. Early galaxies contain abundant gas, but star formation turbulence, mergers, gravitational torques, and feedback all compete to control its motion. The dense environments inferred around little red dots suggest that at least some central regions remain well supplied. The persistence of thick gas close to the black hole is consistent with a phase in which inflow has not yet been fully disrupted by radiation or outflows. Growth also changes the surrounding system. As the black hole becomes more massive, its luminosity can rise if the accretion rate remains high. Stronger radiation increases pressure on the cocoon and can alter its ionization and structure. Eventually, channels may open through which higher energy radiation escapes more directly. Gas may be pushed outward, the covering fraction may fall, and the source may begin to resemble a more familiar active galactic nucleus. This evolution is physically plausible, although direct observational sequences connecting individual little red dots to later quasars remain incomplete. The population, therefore, provides a snapshot rather than a finished story. Some objects may contain relatively small black holes accreting rapidly. Others may already host more massive black holes in dense envelopes. Differences in line width, luminosity, host mass, and obscuration indicate that more than one growth state is likely present. The black hole star interpretation can explain several of these properties, but it does not require every little red dot to follow an identical path. At the deepest level accessible to observation, the central object remains simple in definition and difficult in measurement. It is a black hole gaining mass from its surroundings while gravity converts in falling matter into energy. Everything observed farther outward is shaped by what happens during that growth and by how the surrounding gas processes the released radiation. Current evidence indicates that many little red dots contain actively growing black holes, and that some may be caught during unusually dense, obscured phases of early evolution. Their exact masses, accretion rates, seed origins, and duty cycles remain uncertain, but the measurements increasingly place them within the broader history of how the first generations of massive black holes assemble. Across the immense distance between the early universe and the present, the little red dots remain faint records of a time when galaxies and black holes are still taking shape. Their light travels for more than 12 billion years before entering the instruments of the James Webb Space Telescope, carrying traces of compact galaxies' dense hydrogen-ionized plasma, obscuring gas, and hidden sources of gravitational energy. What first appears as a small red point becomes increasingly layered under careful observation. Faint host galaxies surround concentrated centers. Smooth red continua emerge from compact regions. Hydrogen absorbs, emits, and scatters radiation. Free electrons broaden spectral lines. Dense gas traps energetic photons and releases them again at lower energies. Within some of the best-studied systems, these processes now form a coherent picture of a black hole deeply embedded inside a thick, radiating envelope. The phrase black hole star describes this possibility without removing the remaining uncertainty. These objects are not ordinary stars, and the evidence does not yet show that every little red dot shares the same structure. Some may contain different mixtures of accretion, stars' gas, and dust. Improved spectra, deeper imaging, longer wavelength observations, and future measurements will continue to refine their nature. For now, the little red dots occupy a quiet place between observation and explanation. They show that the young universe contains compact environments capable of hiding powerful sources behind surprisingly cool-looking light. Within that light, matter falls inward, radiation moves outward, and dense gas transforms what distant telescopes finally receive. The smallest red points in Webb's deepest fields therefore preserve evidence of growth occurring behind layers of matter during an early chapter of cosmic history when the first generations of massive black holes are still becoming part of the universe.